All right, section 4.5 is going to finally piece together what we've been doing in the rest of chapter 4, and it's going to bring us back into the notation from the last section in 4.4 combined with what we were doing back in 4.1. So this is called the Fundamental Theorem of Calculus, Part 1. Part 2 is, I think, on the next page. This one says if we have a continuous function on the interval a, b, and capital F is any antiderivative of the lowercase f, then the integral from a to b of f of x dx, so you notice we've got a letter a and a letter b here like we had in the last section, right? They tell us the x values that we're going between, is the same as taking the antiderivative and evaluating at the upper limit b, and then subtracting the antiderivative evaluated at the lower limit a. So what this does is it takes what we did in the last section where we were just working with the context and the description and sort of interpreting what it meant, and it allows us to actually find those pieces of information. Okay? It also tells us that we can go back into section 1 and we can take our function and we can actually find the antiderivative of it and then do the evaluation. Now, the beauty of doing this is that we don't actually need to do plus c on these. And so let me do one where I do the plus c, and you'll see very quickly why we don't need it. Okay? So here's our function. We've got negative 3x plus 4. And what we're going to do first is we're going to take the antiderivative. Okay? So you just did a quiz on this, so most of you are really good at it, and even those of you who didn't pass are doing very well at getting those down. So tell me what we have for the antiderivative of negative 3x plus 4. Over 2,
Plus 4x. Plus c.
And then we would do plus c, okay? So what we're going to do now is we're going to draw a vertical bar at the end of this, and we're going to put the upper limit at 5 and the lower limit 2. And we're going to evaluate this at the number 5. So you have negative 3 times 5 squared over 2 plus 4 times 5 plus the c. And then we're going to subtract evaluating this at the value 2. So negative 3 times 2 squared over 2 plus 4 times 2 plus c. Now before we get too much further, somebody tell me what happens to the c's. They cancel because I've got them both as plus c on the inside here, and I have a subtraction sign between these two quantities. This is the reason why there's no reason to write or no need to write the plus c's when we're doing, this is called a definite integral. Okay, we don't need to do that. So now we're just going to evaluate this at the point 5, or at the x value 5, and then evaluate at the x value of 2. All right, so what happens when we evaluate at the x value of 5? 5 squared is 25, 75, so negative 75 halves plus 20. You can turn that into decimal form if that makes you feel better. And then I have 2 squared. 4 times 3 is 12, divided by 2 is 6. So this is negative 6 plus 8. Okay, so either in decimal form or in fractional form, what do you get when you simplify this? I have a negative. What do you guys have?
It's a negative 31 over 2.
31 over 2. Is that what you guys have? Is Will the only one with the calculator who wanted to calculate it for me? I have a different answer why I'm double checking.
Oh.
But mine may be off though,
I
so
did in my head. It's probably wrong.
it's okay.
Negative 39 over 2.
That's what I have. Negative 39 over 2. Or if you do it in decimal form, what is that? Negative 19.5? Yeah. So either of those forms works just fine. Okay, so far so good? All right, let's do another one. This one we're going to evaluate the definite integral, but we're working with something that has a sign value in it. So what is the antiderivative of the 1 That's x. And the antiderivative of sine? It is negative cosine of x. Very good. And we're evaluating this at pi and 0. So notice I didn't put a plus c on it because, as we established in the last one, it's not necessary. So I've got pi minus the cosine of pi, and then minus 0 minus the cosine of 0. Now, a lot of times when we plug the number 0 in, especially when we're dealing with polynomials, it doesn't end up actually affecting anything. This one it does because the cosine of 0 is not 0. So what is the cosine of pi? Let's start there. It's negative 1. So I've got minus a negative 1, so this is pi plus 1. And then what is the cosine of 0? It's also 1, or it's 1, rather, and then I've got a negative in front of it, so I've got the negative 1 here. So this ends up being pi plus 2. And there's no reason to approximate the pi. We can just leave it as pi. Okay.
Whenever we write these, we don't have to write the c.
You do not need the c at all. All right, let's take a look at the fundamental theorem part 2. All right, the fundamental theorem of calculus part 2 says if f is continuous on the interval ab, so it just starts out the very same way, and the antiderivative is the integral from a to x of f of t dt, then if you were, in essence, to take the derivative of both sides of this, the left-hand side would be f prime of x with a capital F. The right-hand side would be taking the derivative of an integral, and we would simply get f of x. Okay? So what it really looks like, and this isn't quite exactly what's happening, but it looks like the x is replacing this value in here, right? And the integral goes away because we're taking the derivative. So you'll notice on the left-hand side, you have that prime notation. On the right-hand side, there is no prime notation because we had an integral on the right-hand side to start with. It's kind of like saying I'm going to multiply by 5, then I'm going to divide by 5. I'm going to take the antiderivative, and then I'm going to take the derivative. So I get back what I, quote-unquote, started with. Now, in practice, this doesn't work exactly like that, but let me show you what it does do. So here's what we have on this one. What do you notice about this that's different than the description on the previous slide? There is something very different.
There's a variable in the interval.
Well, there was a variable over here. What was the variable? Yeah, this upper limit was x, right? Whereas this upper limit is actually sine of x. Do you guys see that? That actually means something a little bit different is going to happen. So if we were having, like if this function, let me just give you a different one for a moment here. Let's just say that we had g of x equals the integral from 0 to x of t plus 2 dt. All I have to do then is to replace the t with x, and I'm done. That's it. There's nothing else that I would have to do if this simply had an x in the numerator, or in, not in the numerator, but in the upper limit. Everybody okay with that? So let me show you what happens, which is slightly different because there is a sine of x up there. Okay? So what we're going to do on this is we're still going to take and put in the sine of x in for t. But the extra step here at the end is that we need to take the derivative of the sine of x. You know what, let me just erase this from what I had before. So we're finding our derivative here, f prime of x. So what's the derivative of sine of x? That one's cosine of x. And we'll just take one step where we simplify, just distribute this through. So we have sine x times the cosine of x plus 2 cosine of x.
So you multiply the integral.
We're not multiplying the integral. We are taking a derivative over here. Do you see that, Chance? So this piece goes away when I take the when I take the derivative, because I'm taking the derivative of an integral. So it's again like multiplying and dividing by the same quantity. All right? But when I take the derivative, I also have to take the derivative of the upper limit. The derivative of sine of x, which is going to give me the cosine of x right here.
So you just rewrite it and take the derivative.
Right. You're not just rewriting it, but you're evaluating it at sine x, or at the value, upper limit value, sine x. Now the next problem has a slightly different feature going on even than this one. So what's different on number 4? Yeah, that lower value does not say 0, does it? Which is sort of unfortunate because we already knew what to do when it said 0. So let me show you what we do. Do you remember back in, I think it was section 4, right before this one, we had a property that said that if my integral goes from a to b of my function, and there was a c value that was between a and b, that we could break apart our integral so that it went from a to c, and then it went from c to b. Do you guys remember that property? And we had the wonderful visual, or maybe not so wonderful, but we had the idea anyway in a visual form that if we had this sort of in between, if we took this piece and took its area and we took this piece in the area, then it's the area of the whole thing. So we have the ability to break it apart. Well, that's what we're going to do on this problem. We're going to break this apart at the value that we want it to be, which is the number 0. So we're going to take this integral from x to 0 of t squared plus 4 dt plus the integral from 0 to 3 minus x of t squared plus 4 dt. Okay, so the second integral over here actually looks a lot like the last problem. I mean, it doesn't have sine x in that top part, but it looks very much like that, right? I'm going to be able to take the 3 minus x and stuff it in for x, the t, and then I'm going to be able to take the derivative of that piece. But the first piece has a problem. What's the problem? The x is on bottom. And I can't remember if we wrote it or when we wrote it. I'm pretty sure we wrote it. I just don't remember when. But there is a property that we have that says that if our value, and it doesn't matter what the values are here, so I'll put a and b, then I can switch the upper and the lower limits of integration. So I can go from b to a, and it's going to be exactly the same, but the opposite sign. So what I'm working with up here has the ability to do that. I'm going to do the opposite sign and go from 0 to x of the t squared plus 4 dt. And then I have the same second piece that I had before. Now it took us a while to kind of get there because we had several pieces, but the first piece is actually really easy. It's got the negative on the outside, but it goes from 0 to x. It looks exactly like the definition or the theorem says. 0 to x, I've got the t squared plus 4, so what am I going to do? Or what am I going to get? Yeah, I'm just going to get x squared plus 4. And technically, if you want to think about it, you can take the derivative of the x, but that's just times 1, so that's why we don't need this here, so to speak. I don't need that piece of it. So I just get the negative, or the opposite, of the x squared plus 4. On the second piece, I've got to evaluate this at 3 minus x. So I've got 3 minus x squared plus 4. And then I need to multiply by the derivative of the 3 minus x, which is negative 1. And then we're going to simplify and clean this up. So this is negative x squared minus 4 plus, and then I've got to do 3 minus x times 3 minus x, right? Don't tell me that's 9 minus x squared, because that would be incorrect. We are going to get a 9. What else?
X squared plus 6x.
It'll be minus 6x, yeah, and then plus the x squared, you're right. And, sorry, I should have left that in parentheses for the moment, because this is all going to be multiplied by the negative 1 here in a sec. And then I've got the plus 4 at the end, times my negative 1. So this is negative x squared minus 4. This 9 and this 4 make 13, right? So I've got 13 times the negative 1, so I've got negative 13. I've got negative 6 times negative 1, so that's positive 6x. And then I've got x squared times negative 1, so I've got negative x squared. All right, so collect me some like terms. What do I have?
Negative 2x squared minus 6x minus 17.
I think I've got plus 6x.
Oh, plus. Yeah.
And then how much? 17? Minus 17?
So, back on the third step, I think.
Uh-huh.
So, you rewrite your maximum interval.
Are you talking about right there?
Yes.
Okay.
And then you multiply that by the derivative.
Exactly.
Okay.
And you don't have to do that if it's just x as the upper limit, because the derivative of x is 1. But any other value that you would have as an upper limit, yes. And you need the lower value to be, what you really need it to be is a constant for it to work, because when you take it doesn't actually have to be 0, it could actually be any constant and it would be okay. 0 is just nice.
How did we know that 0 was between x and 3?
They're just variables. X and 3 minus x are variables, so the number 0 will be between them for some value of x. Yeah. So we can always split it up there, in other words. Yep. All right, let's take a look at what this means in terms of the last section of material we did. All right, so what we're doing in sort of calculating these quantities, especially those first two that we did, is we're finding the area of a region between some curves. So we're going to actually do that from that straight out standpoint to begin with. We're going to take a curve of y equals x squared, the line at x equals 2, and the x-axis, and we're going to draw a picture of what that visually looks like. So that's where we're going to start. All right, so we have the x-axis. So actually, there we go. I've got the line, or the curve, excuse me, y equals x squared. And I've got the line x equals to 2. All right, so I've labeled the three quantities I have. What we want is we want the area of the region that gets trapped by those three pieces of information. And that area is right in here. Does everybody see that okay? It wouldn't have had to be that. It could be trapped on the left-hand side if we had done x equals negative 7 or something like that. Okay, so there's nothing special about it being in quadrant 1. But we want it to be trapped because of the description of the particular question we're working with. This corresponds, like you saw in the last section, to an integral. An integral, what are my limits of integration, my upper and my lower bounds for this integral? Right, 2 and 0. The farthest left that we go here is 0, and the farthest right that we go is 2. So we're going from 0 to 2. The graph that sort of we are bounding above, so that's going to be sort of underneath that graph, is the y equals x squared. And we're integrating with respect to x, so we put the dx at the end. You did that in the last section, where you sort of gave a visual, you described this, and you wrote that down. But now you have the tools to be able to know what to do with that to actually find the antiderivative. So, what is the antiderivative of x squared? Right, x cubed over 3. And because of the fundamental theorem of calculus, we know we can evaluate that at 2 and at 0. So if I evaluate that at 2, I'm going to get 2 cubed over 3. And this is what I was telling you about just a moment ago, that a lot of times when we evaluate things at 0, they go away. It's one of the nicest places usually to evaluate. This would be an example of that. So the 0 cubed over 3 is 0. But what's 2 cubed over 3? 8 over 3.
How did you know to use the x as
When we were working in the last section, and we had say images like this or graphs like this. When we were doing this, we were looking at the area under the curve, the curve that we are under is the curve y equal x squared. That's why we're integrating with respect to x squared.
So we just pretty much every time just use the y.
Usually, yeah. I mean, like we could be bounding something. Like this said the x-axis, so you have to be a little bit careful because the x-axis is actually the line y equals 0. So there is another y equals here. We didn't see it written quite like that. But it's the curve that we're underneath. And the curve we're under here is the x squared curve.
I was wondering if like the first one was a polynomial and the second one was like a cubic.
We're not going to see that in Calc 1. You will see it in Calc 2. What to do when there's different functions like that, yeah. All right. The last thing in this section is called average value for integrals. So I want you to picture, and I'll use the picture from the last one actually for a moment. Take the image of this, and I want you to pretend like that I've kind of colored it in purple. It looks like on my screen. I can't tell what it looks like from this angle on your screen. You're looking up here. But that piece right there, imagine that it was malleable. So like you could sort of squish it around, okay? So you could take this area that's sort of triangular looking, and you could squish it so that you could turn it into something that looks like a rectangle. Like, so you're imagining something like silly putty or Play-Doh or maybe even bread dough, something that's squishy, okay? Are you with me? What we're going to do, or what we're going to imagine doing, is we're going to imagine putting that into the shape of a rectangle. And what we would want to know is we want to know, well, what would the height of that rectangle need to be? I mean, the width of it is still going to be 2. We're not changing the interval we're looking between. We're just changing the fact that it starts down here at 0 and it ends at 2. So does it level out at 1 in the middle? I mean, like 0 to 2, do I just average the 0 and the 2 to get me a 1? Is that the right value? And the answer is no, it's not always going to be the right value. If we had a straight line, it would be, but on this one we don't. So what we're going to do is we're going to use the average value to find that. So the way we do average value is we do the integral. So you see this integral just like before. But then at the beginning, you actually have this averaging piece. And the averaging piece is 1 divided by the width of the rectangle, or the width of your interval. So in the case we were looking at a moment ago, that would have been 1/2, because our interval had width 2. And our integral that we had found was actually 8/3. So if we had done this for the last problem, the answer would actually be 4/3, not 1. So grab your calculator for a moment, because I want you to actually see that this makes sense from a visual point of view. So take your calculator. I want you to put in the original equation that we had just a moment ago, which was y equal x squared. And I want your window, I do really want your window just to go from 0 to 2 for the x min and the x max. What's that?
Graph it.
And I want you to graph it, yeah. So this is y1. y2, we're going to let be this value that we just found, 4/3. Okay? Does your graph look something like this? Mine's not a very good graph because it's not very convincing even looking at it to me. But do you have a graph that looks something like this? You've got a horizontal line through the middle of it at 4/3. You've got that y equal x squared. Okay. So the idea is that this piece right here fits into this spot right there. Those spots are actually equal area. So if we were to sort of chop off the top of it and reform it, it would fit into that lower corner, and it would be the same amount of space that it was taken up. Okay, that's the average value of an integral. So we're going to do that from the starting spot then for another function. So our function that we're going to do the example for is f of x equals the square root of x. Our interval is going to go from 4 to 9. And we will graph it just like we did on this one at the end, because it's a good way to check and make sure that it visually matches up to what you're expecting. If visually you get something that looks really, really far off, you probably made a mistake somewhere and maybe need to go back and take a look at your work again. All right, so we're going to integrate this from 4 to 9. And out in front of this, because we're finding average value, we're going to do 1 divided by and then it's the 9 minus the 4. Okay, it's just the length, the distance between the two, so it's 9 minus 4. And we've got the square root of x, but there's a much more helpful way to write square root of x when we're taking an antiderivative. It is x to the 1/2, just like when we were doing derivatives, right? Much easier to work with in that form. All right, so I've got a 1/5 at the beginning, yeah? All right, so what's the antiderivative of x to the 1/2? Good. Okay, so I'm going to write it that way even. 2/3 x to the 3/2. Okay, divide by 3/2 or multiply by 2/3. And we're evaluating this at 9 and 4. It might be helpful to recognize that this x to the 3/2 is the same thing as the square root of x cubed. The reason I mentioned that, in fact, I'm going to go ahead and combine the 1/5 and the 2/3 as well, since it's 2 over 15. We'll write square root of x cubed, evaluate it at 9 and 4. This is a helpful way to think about it because we've got the ability to take the square root of 9 and the square root of 4. So I have 2 over 15. I have the square root of 9 cubed minus the square root of 4 cubed. All right, so what's the square root of 9 cubed? 27, that's right. And the square root of 4 cubed?
8.
Good. All right, 27 minus 8 would be 19. So we have 2/15 times 19, which gives me what? 38 over 15. Okay, so as a visual way to check, make sure that you're actually not too far off, so to speak, take your calculator, and what I want you to put in your calculator is the original function, square root of x, and you just need to graph it between 4 and 9. Okay, so from x equals 4 to x equals 9, and if you prefer your, let me write it this way. X min is x equal 4, x max is 9, and then your y min, I would just put your y min at 0 if you'd like, because then you can see the axis down below, and your y max needs to be at least 3, so 3 or higher on that one. And then in y1, you're graphing the square root of x, and in y2, you're graphing the value we just got, which was 38 over 15. All right, so some of you are at that point where you've seen it. Does it look convincing? Okay. This isn't a proof. I'm not trying to say that your graph now, right, that you're looking at proves that this is right. But it would certainly probably show something very off if you were wrong. All right? It should look fairly convincing graphically when you look at this graph. Any questions on that one? Right.